Now we know how to find center of mass for particles if their masses are individually given. Now let us see how to find if the mass is extended or continuous like this. Suppose this is a metal rod. You are asked to find what is the center of mass. Where is the center of mass? So this is an example for finding center of mass of an extended body or continuous body. In finding center of mass of extended body also, we will follow almost the similar pattern. Only thing is, there will be slight modifications. Let us see how to find. We will divide this into number of particles. Suppose if this is origin, this is x-axis. We will divide this into number of particles dm1, dm2, dm3 and so on. These parts are dm1, dm2, dm3 and so on. We can divide as many parts as possible. Then by the formulae which we discussed already, coordinate of center of mass, x coordinate of center of mass will be equal to m1 x1 means x1 into dm1 plus x2 into dm2 plus x3 into dm3 and so on by dm1 plus dm2 plus and so on. So we used the same formula which we derived previously to find the center of mass of extended object also, continuous object also. Now how to proceed further here? This can be written as sigma x dm by sigma dm. Sigma x dm by sigma dm. XCM equal to this. Sigma dm will be equal to 1 by m because it is the total mass of the body. Sigma dm is the summation of all the parts that will give you total mass of the body dm1 plus dm2 plus dm3. If you add all of them, you will get only total mass of the body, that into sigma x dm. Now if sigma x dm, if you consider, if dm is smaller and smaller means if you divide the body into more and more particles, as the number n increases to huge value, dm tends to 0. As n approaches huge value, then dm tends to 0. Then limit of sigma x dm as dm tends to 0 is nothing but integral x dm. Limit of sigma x dm as dm tends to 0 will be equal to integral x dm. Therefore, center of mass x coordinate will be equal to 1 by m integral x dm. Similarly, center of mass y coordinate will be 1 by m integral y dm. Center of mass z coordinate will be 1 by m integral z dm. But remember, for linear object which has only length as measured dimension, only x center of mass is sufficient. If it is two-dimensional object, you will get x and y. If it is three-dimensional object, you will get the three coordinates. So the general procedure to find center of mass coordinate for an extended object is this. For one-dimensional object, only this is sufficient. For two-dimensional object, these two will be there. For three-dimensional, all the three coordinates will be there. Now, this is all represented by a single equation you can represent like this also. Here, this equation represents all the three equations we discussed, xcm, ycm, zcm. So, this will be the relation which is used for extended objects. Instead of coding all x, y and z, we can say this. Position vector of center of mass is equal to 1 by m into integral of RdM. Now, let us see one example for finding center of mass of extended body. Let us take uniform body only. Let us take uniform body of mass m, its length is L. For simplicity, we have taken uniformly distributed mass only. Its mass is m, length is L. Let us try to find where it would have its center of mass by applying this procedure. For this, you take this as origin, choose an element here of thickness dx. So, this element has thickness dx, which is at a distance x from origin. Always follow this procedure only. Select an element dx and find its mass. Mass of this element is dm. So, first step for finding center of mass for extended objects while applying this formula is finding dm. So, find dm. dm is the mass of the element we have chosen here. This element mass dm is equal to mass per unit length. Suppose lambda is mass per unit length for this rod. Let us suppose lambda is mass per unit length. Actually, that is m by L. We will substitute it later. Lambda into dx, mass per unit length into length of the element we have selected will give you the mass of the element. dm you got. Then substitute the dm value here. 1 by m integral x lambda dx. dm is equal to lambda dx, that is equal to 1 by m. Because lambda is constant here, why it is constant? Because the mass is uniformly distributed. So, lambda is a constant, let us pull it out. 1 by m or lambda by m into integral x dx. Now, what are the limits of this integration? Always remember, while applying limits, you should see the total body should come in the limits. The part which is not there should not come into this, the part which is there should not miss in the limits. That means if you take limits 0 to L, it would be sufficient. Suppose if you want to take minus L to plus L, then you are taking this part also, which is not correct here. Only 0 to L is present here, so we can take the limits as 0 to L. This is equal to lambda by m into integral of x dx is x square by 2, 0 to L. This is equal to lambda by m into, substitute the limits, you will get L square by 2. Now, we know that lambda is nothing but m by L, mass per unit length. Substitute it here. So, what we will get is L by 2. This is equal to L by 2. The center of mass is exactly at the center. There is no wonder in this because it is uniformly distributed mass. Center of mass is supposed to be at the geometric center. Nothing to be surprised in this. Now, let us take another example where mass is varying with distance from one end. Suppose this is a rod whose mass distribution is not uniform. When the mass distribution is not uniform, you should get a relation for the distribution of mass. Without knowing any relation, you cannot do. Let us suppose lambda is equal to alpha x. Lambda equal to alpha x, where alpha is a constant. That means as we move from origin towards the other end, for every value of x, lambda is changing. Therefore, mass distribution is not uniform. In this case, what we should do is, the same relation should be applied. X center of mass is equal to 1 by m integral x dm. As I told you already, first to find dm value. Dm will be equal to lambda into dx. You choose an element here which is at a distance x, thickness of the element is dx, then mass of the element dm is equal to mass per unit length into length of the element. Mass per unit length into length of the element. So, this is equal to alpha x dx. This is the mass of this element. Then this will be equal to 1 by m integral x into alpha x dx. If you integrate this from the limits 0 to L, you will get some value, and here mass is not given to you. Directly mass is not given to you. You are given only that mass per unit length is equal to alpha x. You have to get the mass from this relation only. How to get? Mass is equal to integral dm from 0 to L. Mass is equal to integral dm from 0 to L. Integral dm is this. Integral alpha x dx 0 to L. Here if you integrate this, what we will get? 1 by m into alpha into x square dx integral from 0 to L. Here this would be equal to alpha into integral x dx from 0 to L. So, you got the value for the numerator, you get the value for the denominator. In both the values you got now 1 by m into this will be equal to L cube by 3, alpha L cube by 3 into m. I will write it here. XCM is equal to 1 by m into alpha into L cube by 3. Similarly, m is equal to integral alpha x dx, means alpha comes out, x square by 2 will be there, that would be equal to L square by 2. This is m value. XCM is equal to this divided by m. Alpha L cube by 3 divided by alpha L square by 2. So, L cube, this gets cancelled. This will be equal to 2L by 3. That means center of mass will be at a distance 2L by 3 from the origin. So, this is how we find the center of mass for non-uniform distribution of mass. The steps are simple. You write the same thing here. XCM is equal to 1 by m integral x dm. Same formula. Find dm. Then substitute the value of dm here. Then for m, again use the relation. Or you write the formula itself like this. X center of mass is equal to 1 by m. X center of mass is equal to integral x dm by integral dm. You can write like this. Y center of mass is equal to integral y dm by integral dm. So, you can use this relation where you need to find mass also. If mass is already known to us, we can use this, we can eliminate this step. In this particular problem, we are not given any mass or anything, just we are given that mass per unit length of the rod is alpha x. length of the rod, total length of the rod is only given as L. This is only given to us. Then to find the center of mass coordinate, what we have to do is first apply this formula. First find numerator and then denominator. The ratio will be the value. 2L by 3 will be the answer here. So today what we discussed is how to find center of mass for discrete mass distribution, also how to find center of mass for extended bodies. Let us extend this tomorrow.